As we have discussed the problems on time response analysis in the previous class, now today we just focus some problems how they appear in competitive exams on time response analysis. Let us look at the problem 1 given here. Unit step response of the system is given here. It is of first order system, and the tolerance of 0.02, that is 2% tolerance band is allowed here in the steady state, and you are asked to calculate rise time and delay time for this first order system. The settling time is given here 10 seconds and tolerance is allowed 2%. So as the settling time was already defined for 2% tolerance is equal to 4 times time constant for 2% tolerance, and it is given in the problem the settling time 10 seconds. So from this you can get the time constant 2.5 seconds, and the unit step response C of t is given by 1 minus e power minus t by tau, where tau is the time constant. It is calculated from settling time and it is 2.5 seconds, and the delay time, the response C of Td is equated to 0.5 because delay time is the time required for the response to reach 50% of the final response. So equating that to the time response equation, we get delay time as 1.732 seconds. Now the rise time is calculated in this way. It is from 10% to 90%, a overdamped system. So C, that is response at 0.9 and response at 0.1. The difference will give you the rise time because it is a overdamped system, and rise time is given by 2.2 tau time constant, and you will get 5.5 seconds rise time. No peak time exists because it is an overdamped system. Peak time exists only for underdamped system, and no peak overshoot also because it is a overdamped system. Second problem, the impulse response of a unity feedback control system is given by C of t. It consists of exponential term e power minus 3t and sine 4t. Again it is given here 2% of tolerance band. You are expected to calculate all the time domain specification: peak time, settling time, damping constant, undamped natural frequency, delay time, rise time, and peak overshoot. So if you look at the time response expression, this exponential constant minus 3 is related to the real part of the pole, and this 4 is omega d, that is damped natural frequency J4. So the information you get from C of t is, in the exponential constant you have a real term, and this 4 sine 4t means sine omega t. So 4 is the omega d, damped natural frequency. So omega d is taken as 4, and the time constant is reciprocal of this real part of the pole, that is 1/3 seconds. So as we know, the expression for peak time is given by pi by omega d, where omega d from the problem it is J4. So the magnitude of omega d is 4, so pi by 4 seconds is the peak time. Settling time for 2% tolerance band, 4 times the time constant, and its value is 1.33 seconds. Zeta is a damping constant. It is to be obtained from this right angle triangle. So this part cos theta equal to zeta. So theta is obtained from this right angle triangle as 3/5. cos theta. So that itself is zeta, this is equal to 0.6. So 0.6 indicates it is a underdamped system. The value of zeta lies between 0 and 1 is a underdamped system. Now time constant tau is given by 1 by zeta omega n. So from this you get zeta omega n as 1 by 3 because time constant tau is 1 by 3. So from this equation we get the value of omega n as 5 radians per second. So once you get zeta, that is equal to cos theta from the right angle triangle, and omega n undamped natural frequency from this expression, tau is equal to 1 by zeta omega n, you can calculate all time domain specifications. So Td is 1 plus 0.7 zeta by omega n. So zeta is 0.6, omega n is 5 radians per second, it is equal to 0.284 delay time. Next, the rise time, time required for the response to reach 100% of final value. This is to be calculated pi minus cos inverse zeta, because theta is cos inverse zeta and omega d, it is 4 radians per second. So rise time you get 0.55 seconds. Peak overshoot is independent of undamped natural frequency. It depends only on zeta and it is 9.4%. The normalized difference from steady state value to the highest peak is 9.4%. So once you solve the problem, you can actually analyze this. If you get zeta and omega n, all the time domain specifications can be determined. And another observation you can make is settling time is 1.33 seconds and rise time is 0.55 seconds. Delay time is 0.28 seconds. So highest is settling time. In this time domain specifications, settling time is the highest one, 1.33 seconds. Delay time is the lowest one, 0.284 seconds. And rise time next, then peak time, then finally settling time. So you can always cross check that whether you have done correct or not with this way, because settling time is the time required for the response to finally settle in the steady state. Let us move to the next problem. Find the peak overshoot of the following system. C of s by r of s is given by this 25 by s square plus 6s plus 25. For zeta equal to 0, the expression will become like this, because this middle term is 2 zeta omega ns. So that 6s term will not appear in the expression because zeta equal to 0, and for that the peak overshoot is calculated, it is 100%. Means with zeta 0, the peak overshoot is 100%. Now you can see that for zeta equal to 1, the peak overshoot will be 0%, because as zeta increases, the peak overshoot will decrease to 0%. Means zeta equal to 0 means it is a critically damped system, so no question of peak overshoot exists. At 0 it is maximum, zeta equal to 0, the peak overshoot is maximum, but as zeta increases from 0 to 1, so the peak overshoot is coming down to 0. So that is the conclusion of this problem. When zeta increases from 0 to 100%, peak overshoot decreases from 100 to 0. When zeta greater than 1, also there is no peak overshoot because system becomes over damped for zeta greater than 1. Next problem, find the time domain specifications of a unity feedback control system whose g of s is given. This is the open loop transfer function of a unity feedback control system, 25 by s into s plus 4. It is a second order system and feedback is unity here, h of s is equal to 1. So as you know, the closed loop transfer function for this g of s is given by c of s by r of s. It is equal to g by 1 plus gh. So you get 25 by s square plus 4s plus 25. It was explained in the earlier class that when g of s is given 25 by s square plus 4s, the closed loop transfer function will become s square plus 4s plus 25. So this 25 is the numerator term of g of s. So this is added to the denominator. So it becomes closed loop transfer function. So from this expression, you can compare with the standard second order system transfer function. So you get omega n square is equal to 25. So omega n is 5 radians per second. It is the undamped natural frequency is obtained from the data that omega n is equal to 5. And zeta is to be obtained from the middle term in the denominator, that 2 zeta omega n is equated to 4, and you get zeta equal to 0.4. Now once you know omega n and zeta, you can calculate damped natural frequency using this formula, omega n under root of 1 minus zeta square, and omega d you get 4.5 radians per second. You can cross check here itself that omega d should be less than omega n, because omega n is for zeta equal to 0. As you increase the zeta from 0 to 1, then omega d decreases. So the damped natural frequency should be always less than omega n. Now you can calculate all the time domain specifications. Tp is the peak time, pi by omega d, and in the calculator you should choose the radian option, and then calculate the peak time pi by omega d, where omega d is 4.5. So you get peak time as 0.698 seconds. Next, delay time using this formula, you get 0.256 seconds, and rise time is calculated using this pi minus cos inverse zeta by omega d, you get 0.44 seconds. And peak overshoot independent of omega n, but it depends on zeta. It is 25.3%. And settling time at the last using 4 by zeta omega n, you will get 2 seconds. So you can see from delay time 0.256, next appearance rise time, next peak time, and finally the settling time, it is 2 seconds. So this is the way you should calculate the time domain specifications when zeta and omega n are obtained from this second order closed loop transfer function by comparing with standard second order system. The next problem, you need to find the time domain specifications for the system given below. You can see it is a unity feedback control system where g of s is given here 20 by s square plus 5s plus 4. Now what happens to the c of s by r of s closed loop transfer function? So the numerator 20 is added in the denominator. Originally it was 4, now 20 is added, so it becomes 24. But as you know, to compare this second order system with the standard second order function, the numerator term and this constant in the denominator must be same. So here it is not so. So what you have to do is multiply both numerator and denominator by 24. Now 20 by 24 is a constant. It doesn't affect the time domain specifications. So it affects only the steady state value. So we need not bother about this constant at this time and use this standard function that is given in the brackets, and from that you see that what is omega n. and what is zeta by comparing this function with the standard second order system. So you get omega n and zeta. From that you can calculate omega d. It is 4.2 radians per second. Please observe that this value is less than omega n. And as usual, you can calculate the peak time, delay time, rise time, peak overshoot, and finally the settling time. So this observation you need to make always while calculating time domain specifications, starting from delay time, rise time, then peak time, then settling time. So this problem is important to remember that when you have a numerator term is different from this constant in the denominator. So you just see that it should be multiplied and then get the function, and you can compare now this function with the standard second order system. This is another problem. You are asked to find out the unit step response, the system that is shown here, and C of t is the time response. So it is given by 1 minus e power minus zeta omega nt by under root 1 minus zeta square sin omega dt plus cos inverse zeta. This is the response of a second order system for unit step input. So this 1 stands for unit step input, and this rest of the term is oscillatory term. That oscillations are going to die as time approaches infinity. So this exponential decay indicates this term. Oscillations indicate this sin omega dt term. As zeta is lying between 0 and 1, this function will become 0 as time approaches infinity, and this will remain in the steady state as 1. So for this previous problem, you may be asked to find out the time response. As you know zeta, as you know omega n, omega d and zeta. It is only substitution of all the values in the C of t. Let us move to the next problem. G of s, h of s is given by this function. You can see k by 1 pole at origin, then s plus 1, s square plus 2s plus 3. So you may get a question that what is the type and order. So the type means the number of poles at origin. So the type is 1 here. Number of poles at origin gives the type number. This type number has got another significance, that number of integrations involved or number of poles at origin. So there is only 1 pole at origin, so it is a type 1 system, and order is 4, means highest power of s in the denominator, or the number of poles of the given function. The number of poles are here 1, 2 and 2 complex poles. So the number of poles are 4, so the order is 4. Number of poles at origin indicates type number. Number of poles of the whole function indicates the order of the system. You can just look at given problem. Here also you are asked to find out the type and order. As if it looks 4th order, but type number, it looks like there is no pole at origin, but it is not so. It is a type 1 system, means there is 1 pole at origin. You can see here the last one is not a constant. So you can take s out from this denominator. That indicates there is 1 pole at origin. Then the rest of the function becomes s cube 3s square plus 4s plus 20. So the type is 1 because there is 1 pole at origin, and number of poles of the function are 4 only, so the order is 4. This is the next problem that appears in time response analysis, that C of t is given by this function 1 plus 0.2 e power minus 60t minus 1.2 e power minus 10t. This is the response. For what input? R of t equal to 1, that is unit step. So response is given in time domain and input also is given as a function of time. It is 1 unit step. So you are asked to calculate the damping constant and undamped natural frequency. So we need to apply Laplace transform for this C of t. So 1 becomes 1 by s, 0.2 e power minus 60 term becomes 1.2 by s plus 60 and this term becomes 1.2 by s plus 10. Similarly, R of s input also Laplace transform is applied to the input function. It becomes 1 by s. Now it is you need to calculate the transfer function C of s by R of s given by this function. So you can see now the C of s is given by 600 by s square plus 70s plus 600. Now compare this with the second order standard system. This is the standard function of the second order system. So you get omega n square as 600. So undamped natural frequency is 24.49 radians per second. And to calculate zeta, you compare this 2 zeta omega n with this 70. You get zeta as 1.43. This indicates the system is overdamped because the value of zeta is greater than 1. So you asked only zeta and omega n. No need to calculate all the time domain specifications. Of course, once you know zeta and omega n, you can calculate all the 5 parameters which we have seen in the previous problems. But here he asked only to calculate zeta and omega n. Another variety of problem that appear in the time response analysis is k. Constant is not given, but he has indicated k by s into s plus 10. It is a second order system. So calculate the value of k for zeta to have 0.5. Means assume that it is an underdamped system with the value of zeta equal to 0.5. Calculate the value of k. This is another variety of problem that appears in time response analysis. So you can use this formula to calculate closed loop transfer function. Using this formula, you get k by s square plus 10s plus k. So when you compare with the standard second order system, you get omega n equal to root k and 2 zeta omega n is given by 10. So from this you can calculate omega n because he said the system assume that zeta of 0.5, then you can calculate undamped natural frequency as 10 radians per second. So once you get omega n, now k you can calculate using omega n square. So k is equal to 100. It means that for this system to have a zeta of 0.5 means for having the poles of these two in the complex conjugates, the value of k must be 100. So when you choose 100 by s square plus 10s plus 100. Now if you see the roots of this equation, you will get complex conjugate pair. Indicates that it is an underdamped system because the zeta given 0.5. This is not a electrical system. He has given a rotational system example. In this problem, it is second order system anyway because there are two roots for this transfer function and theta of s is angular displacement in radians per second and T of s is the torque. So output by input is 1 by this function. where J is the moment of inertia and B is the rotational friction coefficient and K is spring stiffness. And the force, of course here torque, is given by 10 Newton meters. So that is given, input is given. Now he also gives that the peak overshoot of the response is 6% and this peak overshoot exists at 1 second. That means peak time is 1 second, and steady state output of the system also he has given 0.5 radians. It settles. Then find all the three rotational mechanical system constants: moment of inertia, friction and spring stiffness. So input is given as 10. You can consider it as a step input. So Laplace transform of the torque is 10 by S. And you can now see the theta of S is given by this function because T of S is taken to the right hand side, and that is 10 by S, the torque, Laplace transform, and rest of the function as it is. Now the steady state output of the system is given 0.5 radians per second. According to final value theorem, limit t tends to infinity, f of t is equal to limit s tends to 0, s into f of s. So this steady state output can be written as limit s tends to 0, s into theta of s, and that is equated to the 0.5 because the response settles at 0.5 radian, and from this you can get the value of k as 20 because you substitute s equal to 0, this term goes 0, this term also becomes 0, s and s gets cancelled, so k remains. So the spring stiffness is obtained from this function as 20. Now peak overshoot is also given in the problem. 6% means 0.06, that is equated to the expression e power minus zeta phi by under root 1 minus zeta squared. From this you can calculate zeta and it is 0.667. Remember, it is an underdamped system, and the peak time also given as 1 second. So from this you can use this formula pi by omega d, and you can get omega n from this as 4.21 radians per second. So the second order system denominator, you can see here, it can be written in this way to compare with the standard second order system. So you get omega n as root k by j, and from this you can calculate j because k is known 20 and omega n is also known 4.21. So substitute, you get another constant called moment of inertia 1.128 kg per meter square, and use this second term in the function 2 zeta omega n with b by j, and you can calculate the other constant that remained as b, friction coefficient, get 6.34 Newton meter per radian per second. So this is the way you may be asked to calculate the system parameters like j, b and k. This is the way you should actually calculate. This is another variety of problem. It is given in the form of differential equation. The same second order system, d square y by dt square, 4 dv by dt plus 16y equal to 16x. Y is the output, x is the input, and you are asked to calculate the zeta omega n and peak overshoot for x of t equal to 1. So apply Laplace transform to this differential equation and then simplify that. You get the function 16 by s square plus 4s plus 16. This you need to compare with the standard second order system. You get omega n as 4 and zeta as 0.5 and peak overshoot is 16.3%. So this is an underdamped system because zeta equal to 0.5. Unit step response we need to find out, and settling time also to be calculated, both for 2% and 5% tolerance. The definition of settling time is the time required for the response to reach and stay within the tolerance limits. So 2% and 5% are to be considered to calculate settling time. So system is given in the form of pole zero diagram here. You can see here there are two poles in this system, complex conjugate pair. One is at -4 plus G2, this one, and the other pole is at -4 minus G2. So this is the example of underdamped second order system, and this is the real part of the pole and this is imaginary part of the pole. You are asked to calculate the settling time. So the two roots of such function for underdamped system given by this function minus zeta omega n plus j omega n under root of 1 minus zeta square. So this is the real part. This is the real part of the pole minus zeta omega n, and this is the omega d, that is imaginary part of the system. So it is given in the problem that real part of the pole is at -4. Equate this to -4 and equate this to imaginary part 4 and get omega n under root 1 minus zeta square equal to 2, that is given in the problem omega d radians per second. So from this you can actually get the value of zeta as 0.894 and omega n is given by 4 by zeta. You get 4.474 radians per second. You can see that always this omega n should be more than omega d, because omega n is natural frequency oscillations of the system without any damping factor, that is zeta equal to 0. Once you introduce zeta, some value, then omega d comes into picture, it will be definitely less than omega n. So now you can actually give an expression for time response of the second order system that is indicated. As you know zeta, as you know omega n, just substitution in this expression 1 minus e power minus 4t by this 0.447 is under root of 1 minus zeta square. Sin omega d is 2 from the problem itself plus tan inverse under root of 1 minus zeta square by zeta. So this is the way you should express the time response of a second order system, which includes the steady state value of 1, and this remaining part is the oscillations, damped oscillations, which are going to die as time approaches infinity. So the total time response consists of two parts, steady state part 1, and this is a transient part which is not going to be there for longer period. Practically 4 to 5 time constants is sufficient for damping out these oscillations. And now you can calculate the settling time, as I said, 4 times the time constant. So waveform will settle, means the response will settle in the steady state. So this is to be calculated for 2% tolerance and 5% tolerance. So it varies. If you use 2% tolerance, it is calculated using 4 by zeta omega n. If it is 5% tolerance, then it will be 3 by zeta omega n. Settling time is 4 seconds. Another variety of problem that is given as mechanical vibratory system. It oscillates when the force is applied as shown. You can see it is a translatory mechanical system. It consists of mass and the spring constant K and friction component, that is damping factor beta, and it has a linear displacement of x. So it is a translatory mechanical system. Translational motion means linear motion system having x as a linear displacement. Such a system, when excited by some force, then it has a response of this way. You can see it is a second order system under damped response, and the waveform is settled at 0.1, and the force applied on this is 2 lbs. You can see the peak overshoot as 0.095 and settles at 0.1, and the peak time is given as 2 seconds. This is the time required for the response to reach the highest peak. So it is 2 seconds. This is the data given, and you are asked to calculate frequency of oscillations omega n and omega d. So you can use the differential equation approach even to the mechanical system. So P is the force applied equal to mx double dot. This is acceleration term, this is velocity term, and this is displacement term. So x double dot, x dot, and x. The constants involved here: mass, friction component, and spring stiffness. Apply the Laplace transform to the differential equation of a mechanical system, and then obtain x of s as output. P of s is the force that applied here, transfer function. It is given by this system again, and the input force applied on the mechanical system is given 2 lbs. It's like a step input. So the Laplace transform of this P of s is 2 by s. Now you get x of s, substitution of P of s in this function, you get x of s like this. Now from the graph it is given that the response is settled at 0.1. So x of infinity indicates steady state response after transients have become died out. So limit s tends to 0, s times x of s is, according to final value theorem, that is equated to 0.1. Equate the function to 0.1 and get the constant k as 20 lb for ft. Then calculate mp, because you got zeta, and the peak overshoot of the second order system was given in the graph as 0.095. So you can calculate zeta from this expression, because peak overshoot depends only on zeta, not on omega n. So get zeta by equating peak overshoot to the 0.095 which was given in the graph of this problem. Now peak time also given 2 seconds to reach the highest peak, 2 seconds, and the expression for peak time is pi by omega d. That omega d is given by omega n under root of 1 minus zeta square. You got zeta as 0.6 here. So now equate this to 2 seconds peak time given in the problem and get omega n as 1.96 radians per second. So this is the way you should calculate the zeta and omega n even for a mechanical system. There is no much difference between an electrical system and mechanical system. We have discussed in the previous classes, any system, as a matter of fact, can be described by a differential equation. Once you get this differential equation using Newton's laws of motion, apply the Laplace transform, get the transfer function, apply the input, and equate the given response to steady state value of 0.1, and then get zeta and then omega n. This is the way we should solve the problem even for mechanical system given. This is another problem given of a mechanical rotational system whose g of s is given by k by s into js plus f. a second order system. And you're asked to calculate zeta and omega n. 4 options are given here, A, B, C and D. The first one is zeta, the second one is omega n. So which one will suit to this particular problem we need to see. So for the given mechanical system, we need to obtain the transfer function with the output and input ratio. Then we need to compare this function with the standard second order system. So omega n is given by root k by j. And once you get this option, 80% of the problem is solved. You can see the options. So this omega n root k by j is only in option C. So you need not calculate the zeta. Directly you can put the option C because omega n is root k by j appears only in C option that is actually given. However, you can still calculate zeta 1 by 2 f by root kj. So answer is C. Option C is the right answer. Now the questions may appear in this form, like a unity feedback control system has g of s given by this second order function. Then what is undamped natural frequency? So as you know, this numerator term is omega n square. So omega n is 4. Omega n is 4. So option D is the right answer. You will get when you compare this with the standard second order system, you get omega n equal to 4. So option D. You have another problem. G of s is given by this function. It is excited by a unit step input of r of s equal to 1 by s. So the steady state output is. So we need to calculate according to final value theorem, limit s tends to 0 s g of s. G of s is given here, substitute, and then you get the steady state output as 0.4. Now this is another problem. You can see that function is given in the form of various blocks. This one is multiplied by with this because these two blocks are in cascade. So together the product is G and this is H. And he asked the question, so simple, what is the type number? So you need not solve this problem. Only thing is you should identify the type number by looking at the function which has how many poles at origin. So you can see here there are no poles at origin here in the denominator. There is one pole here in the denominator and there is one pole here in the denominator. So 2 poles, so it is a type 2 system. Remember, you need not solve this complete one, but only thing is you should identify that how many poles are there at origin. So 2, so the type of the system is 2. This is another problem of a mechanical rotational system. The block diagram form it is represented, and you are asked to calculate the constants k and kn so that the maximum overshoot means peak overshoot in the unit step response is 0.2 and the peak time is 1 second. So that peak overshoot is appearing at Tp 1 second. With these values of k and kn which you obtain from this data, you need to calculate the rise time and settling time. It is also given the moment of inertia J as 1 kg meter square and the friction coefficient as 1 Newton meter radian per second. This is the data given which help us to calculate the rise time and settling time. So get the function first, C of s by R of s. Compare this with standard second order system. Get omega n as root k and zeta also damping coefficient by equating this s coefficient with the standard second order system. Then peak time is given by pi by omega d this must be equated to 1 and get omega n as 3.53 radians per second. And peak overshoot is given in the problem, that is 0.2 above the steady state value. From that, zeta is to be calculated. So you get zeta as 0.456 under damped system. So peak time 1 second was given in the problem. Equate this function to 1, get omega n. Then peak overshoot was given in the problem 0.2. Equate to this equation and solve for it, get zeta 0.456 seconds. Now once you get zeta and omega n, you need to get k as 12.5 and equate zeta to this function. K is known, zeta is known. Calculate now kn. So kn is 0.178. So this is the way when problems of mechanical rotational system with k and kn, some constants, how to obtain. Then you can calculate now rise time using the formula that was actually given in the previous problems too. And settling time is to be calculated. You need to look at whether it is tolerance is considered or not. Default, you should use the formula settling time equal to 4 by zeta omega n. This is for 2% tolerance. Remember, if it is a 0% tolerance, then instead of 4, you should write 5. If it is a 5% tolerance, instead of 4, you should write 3. Denominator remains same. So it is only how much tolerance you are allowing. No tolerance, then it takes more time. So 5 time constants for settle the response. 2% tolerance means 4 by zeta omega n. 5% tolerance means 5 by zeta, 3 by zeta omega n. So settling time is calculated and you get 2.48 seconds. This must be greater than the rise time. For cross-checking your answer, settling time should be the highest time for the response to settle, because transients and everything must have to die. It is also given here for 5% tolerance. As I said, you need to use this expression 3 by zeta omega n, and it is 1.86 seconds. Means 5% tolerance means it is still early, so you have got 1.86 seconds. But 2% tolerance means it is taking still more time, 2.48 seconds. If you say 0% tolerance, then it will be greater than 2.48 seconds. Remember, all these settling times must be greater than the rise time.